Hi everyone, uh, I'm Stéphane Marchesin and I work on ChromeOS graphics. And today I'm going to walk you through the basics of ChromeOS graphics in this presentation called ChromeOS Graphics 101. So let's get started. So the goal of this presentation is to provide a high-level description of all the critical components used by the ChromeOS graphics stack. Following this description, we will also walk through a few concrete examples, like a few end-to-end use cases that will allow you to better understand how the different components fit together. So without further ado, let's take a look at a concrete overview of Chrome OS. So this is a screen of Chrome OS running. And as you can see, we're displaying multiple windows. On top, we have a web page, right? A simple web page like we know and love. But behind it, we have other things. We have a Play Store application, right? An Android application running on Chrome OS. And behind it, there's another thing, which is a Linux-based code editor, right? Uh, how does that all come together, right? How do all these different ecosystems and applications come together to produce a single screen? And so the goal of this whole slide deck is to walk you through how all of this is accomplished. So let's start with a super high-level view of how things line up, okay? Here's a diagram, and I know it looks a bit complicated, but we're gonna slowly go over it and we'll explain every part. This diagram shows all the major components that you will find in the Chrome OS graphics stack. Let's start on the top left. On the top left, Arc++. Arc++ is the Android implementation in Chrome OS. It allows us to run Android applications on our platform. On the top right, we have Crostini, which is the code name for our Linux application support, or we saw earlier the Linux application. This is called Crostini. This is a virtual machine. And then in the middle, we have obviously the web-based, right, the renderers, etc., which is how we actually view web content on Chrome OS. So you see there's a hint here in how the diagram is laid out about these three stacks. At the very bottom, we have the hardware level, right? And as we go higher and higher in the stack, we're getting closer and closer to the application level. And so that's actually what we're going to do. Following all this, the first part of this presentation, we're going to walk from the bottom of the stack at the hardware level, layer by layer, and looking at what's going on in each of these layers. So let's get started. Let's start with the hardware level. So the hardware. The graphics hardware has many things in it, right? What we typically call a GPU or a graphics processor is actually a collection of different hardware units. There's three main units. They are the 3D engine, the video engine, and the display engine. So let's see what each of them does. So first of all, the 3D engine. A 3D engine takes a description of the geometry of a scene, right, that we see on the graph here in terms of numbers. It's basically done as numbers, which represent triangles, texture coordinates, colors, etc. So all these numbers represent all that geometry. And it takes that and renders it, all these triangles, into a buffer of pixels. So we basically take that geometry, which is 3D, and flatten it into a buffer of pixels. And so this is what's shown here. We have three triangles, red, green, and blue, described as a set of numbers. If we take the perspective of the buffer, right, the whole pipeline there is going to be kind of a producer-consumer. And in that perspective, the 3D engine is a producer of buffers, right? We'll see later we also have consumers. But the 3D engine is a producer of buffers, right? It makes buffers based on other information. So that's the first unit that we have at the hardware level. The second unit is the video engine. The video engine, what does it do? It takes an encoded video data stream, so represented as bytes typically, which we see on the left of the figure here, and it converts it again into a buffer of pixels that actually is one frame of the video that we're looking at, that we're decoding. So the video engine, in a way, is also, in that producer-consumer of buffer mentality, is also a producer of buffers. Note that there is also the reverse. There's a video encode engine, so we don't only go from the left to right, right, to produce frames from data. We also have another unit that can go from right to left, take the images and turn them into a stream of bytes. Then we can, for example, pack those bytes over the network and send them. Typically, this is used when you're video conferencing, over Meet, for example. For more details on the video stack, we're not going to go too deep, but there's going to be a talk tomorrow about all of this called Life of a Video Frame, which I warmly recommend. And the third engine at the hardware level is the display engine. The display engine, what does it do? Well, it takes one or more buffers in memory, and it presents them on the screen. So in this case, remember we had the 3D engine producing these buffers of triangles earlier, right? Well, now we kind of want to show it on the screen. What are we going to do? We're going to ask the display engine, please show it on the screen. What it can do is take multiple events, so not just our application with our 3 triangles, but also our user interface. Here we have an example, right, with the whole user interface, the icons, etc., that surrounds the window we care about. And it will flatten it and put it as one single buffer on the screen and show it. If we take our metaphor again of producer-consumer, the display engine is actually a consumer of buffers, right? It will take those buffers and consume them into showing it to our users. So that's it for our hardware. Let's take a look at the software stack. And the first level of the software stack, the first stop, is the kernel. And in particular, what's interesting here is the kernel graphics subsystem called DRM. So what's DRM? DRM stands for Direct Rendering Manager. It's not to be confused with the digital right managements, which has nothing to do with that. It is an API that allows user space Linux applications to control the display, submits commands to the graphics hardware, right? This term DRM will be used throughout the slides, and you'll probably find it everywhere when you work on Chrome OS graphics. So it's important to know that it refers always to this kernel API. One part of DRM that is important is called KMS, and I have it at the top left. I say DRM/KMS. KMS stands for kernel mode setting. This is the specific bit of DRM that allows us to configure displays. So, if you have a certain number of displays, how do you configure them? How does this, what do you display on them, etc. And so the DRM KMS subsystem at super high level, it allows two main crucial functions. The first one is what we just talked about, displaying multiple buffers on the screen. This is done through what we call the Atomic Display API. It is called Atomic because it allows an application to update the configuration for many pieces, let's say multiple overlays, multiple displays, etc., in one single atomic unit. So we can say, I want to configure all those things in one single go, and I want to make sure that they get affected all together, right? And have guarantee on the consistency of the outcome. So that's the first crucial function. The second crucial function that we will see throughout all of these adventure in the graphics stack is the buffer sharing capability, right? We need to be able to create buffers. We need to be able to share buffers between multiple processes and multiple subsystems. And this is done through what we call a DMA-buff framework, DMA buffer framework. This framework is great because it allows us to pass buffers between processes and subsystems bypassing just a file descriptor, right? So we just abstract the buffer as a file descriptor and give it to some other subsystem or give it to another process. And this is done without any copy, so this is very efficient, right? For example, if an application somewhere produces a buffer and somewhere else we have a consumer, right? Remember the producer-consumer metaphor? If we have that, ideally, pipeline, there would be no copies of all the content at each hop. Right? We can take the exact same data and give it to the next one in the chain. And that's what we do here. Why is this so crucial that I focus so much on not copying? Well, because a single buffer for a 4K display is 32 megabytes of memory, right? And we go through about 60 buffers per second when we are animating. So like copies are completely off the table. They would make us unbearably slow. So the second mechanism that we care a lot about is this zero copy buffer sharing called DMA buff. Now let's look at our user space drivers. So the first user space driver is mini-GBM. What is mini-GBM? Well, it's an abstraction of memory allocation. It provides a mechanism for applications to allocate buffers. And primarily, this is for the GPU, video, camera subsystems. So what we can do is that the application can request use cases that it wants to have. For example, it says, I would like to have the camera I would like the camera to be able to use that buffer, or I would like the display subsystem to be able to use that buffer, or any combination of these subsystems. For this, mini-GBM will look at what use cases you need, and we'll pick the optimal format based on what you want for this job. There's another mode where the application can also request a specific format, which we call modifier, right? Modifier is a descriptor of the underlying buffer format. Typically, it does this because the application has a specific use case in mind. One example is if the display can only consume, right? Again, the producer-consumer metaphor, if the display can only consume a given modifier, then the application can say, I would like to specifically allocate with this modifier so that the buffer I'm allocating can eventually be consumed by the display subsystem. So that's another key element. And the mini-GBM API also provides the buffer sharing. We talked about DMA buff earlier. Mini-GBM provides this functionality in terms of function calls, not IRTLs, to the applications, which again simplifies our life quite a lot. Mini-GBM has a number of backends. So we have backends for each of the hardware platform we care about. For example, on Intel or on AMD or on Rockchip, etc. We have each platform has its own mini-GBM backend here. And so mini-GBM hides the platform specificness of all this. The next step in the driver, in the user space driver side, is the GLES and Vulkan drivers. So all the machinery to drive the 3D engine is fairly complex, right? And this is something that is provided by the OpenGLES and Vulkan drivers. So what are these drivers? Well, they are simply user space libraries which sit on top of the kernel and provide an API to access GPU functionality. These APIs, they allow us to take a series of rendering commands at a high level and effect these rendering commands through the GPU into buffers, right? So we talked earlier about what the hardware can do, right? The 3D hardware takes a set of geometry, turns it into buffer of pixels. This is the API that lets us do exactly that, right? And what's interesting is that at this level, through these APIs, the hardware details are hidden. So Vulkan and GLES, these APIs are abstracting the hardware entirely. So you can write once and run on every possible GPU in the world. Let's talk a little bit about how the consumers of GLES and Vulkan are in Chrome OS. So all the GPU access on the Chrome side is done through a special broker process we call the VIS process. This is done, so it does all of this on behalf of each tab. So every time you open a tab, the tab that you open does not have direct access to the GPU. It calls the VIS process, say, hey, can you please do this on my behalf, this rendering? The VIS process does this and then returns the result, right? This is done for a couple of reasons, right? Mostly this is for security, right? We do not want to let any arbitrary web application access your GPU for security reasons. One of the aspects that's interesting about the GPU or VIS process is that we can actually recover from a crash there. So we can survive, Chrome OS can survive a crash and just pick it up where we left off. For virtual machines graphics, so Crostini, Linux applications, there's a similar mechanism where we virtualize the GPU. Let's talk a little bit about how this works. So in the guest, we have a library called Virgil, which takes all the 3D calls like that we talked about again, serializes them, right, into a FIFO, and then on the host, we have the counterpart, which deserializes those 3D calls. and it executes them on behalf of the guest. And then when we have a result, we send it back to the guest, right? So in the Chrome model, we have two processes, right, that talk to each other. One is, a client to the other. With the virtual machine model, we have a host-guest discussion, but the conceptual idea is very much the same. In the case of Android applications, we currently run in a container, right? So we have direct access to the hardware. What does this mean? This means that each Android application has access to directly GLES and Vulkan at the driver level, and it also means we need two instances of the Vulkan and GLES libraries, right? One is for the Chrome OS system, and one is for the Android system. This will change once Art++ migrates into a virtual machine, and we'll move to a model more like the previous bullet point for Crostini. So now that we've looked at the driver, let's look at Ozone DRM, right? Which is the first component that is actually a part of Chrome in this whole stack that we're looking at. So what is Ozone? Well, Ozone is a Chrome layer whose job is to abstract the low-level platform parts away from Chrome, right? So this was done for ease of portability, right? To hide all those platform-specific. Chrome supports many platforms, and you don't want to have to know about all the details of each platform, right, as you write the higher-level code. So in the specific case of Chrome OS, our Ozone implementation is layered on top of DRM. This allows a lot of different things. Configuring monitors, allocating buffers, right, synchronizing graphics, and using display overlays, right? So all these features are abstracted by Ozone, and then we give it to the high level. For the Chrome OS case, this is all done on top of DRM and OpenGL. And so, as you can imagine, Ozone has many other platform-specific backends, right? But they're not really relevant for the context of this talk, given that Chrome OS only uses DRM there. The gist of it is Ozone abstracts the platform-specific concepts into the higher-level concepts. Right? That's the gist of it. If you need to work with Ozone, that's what it does. Let's move a little bit higher on the Chrome side. Right? Let's look first at the Chrome compositor. So the Chrome compositor, it takes multiple sources, multiple images, right, and flattens it into a final image. So that includes all the windows and all the surfaces, right? We saw earlier the example of the Android application, the Linux application, as well as the web apps, right? All of this came together in one single window. This is the compositor that pulls all of this together and produces the image that we want to see on the screen. Chrome can do this either using display overlays, right? So display overlays are a number of layers that the display itself can support, like we talked about earlier. It can do this if we have enough of overlays, right, in terms of number of overlays and enough overlay features for what we want to support. But if it doesn't, Chrome can also do this using OpenGL. It also has to fall back to OpenGL for effects like blur effects, right? So really, depending on what we're trying to composite and how we're trying to do it, we will use one or the other. Obviously, an overlay is more efficient because the hardware does it for almost free on the display side, whereas OpenGL will incur an extra copy, right? Which, as we've seen by now, I don't like so much. So, we're always trying to trade off between functionality and performance and trying to find how can we fast path the use cases we care a lot about using overlays, right? So this compositor has an interesting tidbit of history. It was initially created only for compositing web pages. So the goal of this compositor was initially just, we have a web page with a number of layers, and we want to flatten it. What are we going to do? Well, that was the first reason this compositor was written. But later it was extended to support not just a single web page flattening, but the entire UI of Chrome OS, including all the windows, right, that came from Android, that come from Linux applications, etc. All of this in one single place gets composited. Note that this compositor is in the process of being migrated to the Skia compositor. The Skia compositor basically uses Skia, which is a rendering library, as its backend instead of using OpenGL, right? But the gist of it remains the same. this compositor either try to use overlays, right? And if we can't, we fall back to the Skia version. So that's for the Chrome compositor. Let's look a little bit quickly at the UI on top of that. So the Chrome OS UI we call shell or Aura shell or Ash. You often will see the term Ash or Aura shell. It's a Chrome OS compositor client, right? And it takes advantage of the features provided by the compositor. And it implements a number of higher level features there. These features include like window frames, right? So when you're in Chrome OS, the window decorations around the windows are actually done by Ash, right? It implements drop shadows, right? The little shadow you see under your window, same thing, done by Ash. The wallpaper, right? The launcher bar that you have at the bottom, all of these, widgets that you click. This is all done at the Ash level. Another class of things that we do in Ash is all the effects. When you go into overview mode, or when you have the window maximize and minimize animations, all of this is provided by Ash. So let's look at Exo now, which is short for Exosphere. Exosphere is a component that allow all the non-web application, non-Chrome native applications to display their buffers in Chrome OS. And as you can see on this diagram, right, this is kind of the entry point for the non-web applications to plug into Chrome OS display, right? So Exo, what does it do? It sits on top of the compositor and it basically feeds external application, right? And it allows us to display them seamlessly into Chrome OS. The way this works is that on one side, Exo implements the Wayland protocol, which is a display server, which allows application to connect to it and request to show buffers. On the other side, with all the surfaces that it has gotten from the Wayland side, it takes those buffers and the surfaces and injects them into the compositing tree. And so the compositor we saw earlier takes, yes, all the rendering scene graph from all the web pages, but also this gets augmented with all the windows that come in from Crostini applications, from Arc++ applications. So we basically have a Wayland server implementation there, and it has some Wayland extension for Chrome OS specific features, for example, display scaling or window frames or blending. But other than that, this is pretty much the standard display protocol. So finally, well, not finally yet, next component in line is Arc++. Arc++ is the name of the Android application support for Chrome OS. Let's look quickly at how does this work in terms of graphics. So Arc++ really embeds a full Android system, right? It's an entire Android system that we embedded into Chrome OS. And that includes Surface Flinger and Hardware Composer. So Surface Flinger is the display server for Android, right? It's the standard display server for Android. And Hardware Composer is the standard backend for that display server. So in the Chrome OS case, we took, instead of the normal case that Android does, which is Hardware Composer talks directly to the hardware and programs the hardware to display the buffers you want to see, what we did is different. What we did is we take the buffers in Hardware Composer and we turn around and we pass them to Exo and say, hey, please display this on my behalf. So for Chrome OS, really, the Arc++ implementation of Android as a display server is mostly a pass-through that turns around, talks to Exo, which itself will go to Chrome, right? Again, all of this is done using DMA buff. So there's no copies anywhere in this pipeline, right? The application produces the buffer, right? The Android application produces the buffer, turns around to Surface Flinger without a copy, passes that buffer. Surface Flinger turns around to Exo, passes that buffer, and then as you get inside of Chrome, Chrome integrates that buffer into the compositing tree and boom, goes down to the hardware the displays. Another aspect of Arc++ graphics is the GPU memory allocation, right? Gralloc is the standard on Android for implementing GPU memory allocation, but what do we do on Chrome OS? Well, on Chrome OS, we've simply implemented Gralloc on top of our mini GBM buffer allocator. This means that we can reuse all the drivers that we already had that we talked about earlier. We can just put a different front end on top of them, and we're good to go. And finally, the last component is all of the GLES, sorry, and Vulkan that we use for exposing the 3D acceleration. Currently, these drivers, they run natively in the container. In other words, like I said earlier, we have a second pair of GL and Vulkan drivers inside the Android container, right? With a little bit of a different Windows system integration, but otherwise they're very similar to the host side driver. And finally, let's look at how the Linux Crostini application works. So Crostini is the code name for Linux application support on Chrome OS. And this is different because this runs in a virtual machine. So because we are in a virtual machine, we fully virtualize the graphics hardware, including the 3D and the display engine in a fully secure fashion, right? This is done with a technology called Virgil. So like I said earlier, it serializes the GPU commands into an intermediate language and then subsequently executes this on the host, right? On the actual GPU on behalf of the guest. So we have this system where the GPU is accessible on the host side, and the guest can, through a hypercall, request things to be rendered for itself by the host. So you say, hey, host, can you please help me render this? And the host goes like, okay, let me go and talk to the GPU and do it on your behalf, and then returns the results. For the display part, it's a little bit different from Android, but the idea is the same. We run the standard X11 Wayland display server inside of the virtual machine. And that thing, again, turns around and talks to Exo and says, hey, please show that buffer on my behalf, right? So we have essentially turned both the Android and the Linux ecosystem into just pass through as far as display is concerned into the Exo and the Chrome compositing stack, right? And again, just like with our plus, all of this is done transparently and without any copy, right, through the buff. So no copies whatsoever. That would slow us down way too much. So now that we have seen all the pieces, let's go over a few things that happen with graphics and display in Chrome OS. And the first one that's interesting to look at, and really the basic one, is what happens when we look at an HTML page in Chrome OS, right? So just only the web for now. So let's follow the life of our HTML page as it gets rendered and displayed in Chrome OS. So we start on the top left of this diagram, right? And the web page JavaScript or HTML triggers a repaint in Blink. Blink is our web engine. Blink will take the content that needs to be rasterized. So for example, you are scrolling, right, in a page. Blink will say, oh, I need to render this part that is being scrolled into the view. And to do that, it converts them into a bunch of Skia commands, or we talked about the Skia rendering library, right, which is a library that abstracts all of the high-level rendering. For example, hey, render a rectangle or render a text at these coordinates, right? It abstracts this at a very high level on top of OpenGL and on top of Vulkan, right? So Blink turns around, prepares those Skia commands, and passes them through to the Viz process. The Viz process will take those commands and will render them on the GPU, right? Again, on behalf of the renderer. You see, there's a lot of delegation there. On behalf of the renderer, we'll actually go and affect them on the GPU. So we rasterize the pieces of the web page that we need to rasterize with the GPU, right? Which is the GPU raster stage that we see here. So we go down the stack to the hardware, come back up, sorry. And then come back up with our buffer of pixels. Once we have our buffer of pixels, we turn to the compositor and say, hey, please, now I have my frame. Can I display it? And the compositor puts all of the buffers together, right, including potentially all the other renderers and all the other windows and all the other UI that he has to, account for, and then flattens all that, right? We talked about it using either the GPU or display overlays, and it asks Ozone DRM, please show this for me. I want to show these surfaces at these coordinates. Here are my set of surfaces, please show them. And then Ozone DRM knows how to program the kernel DRM subsystem, which it does, right? It asks the kernel DRM driver, please do that for me. The kernel DRM driver effects these changes into the hardware, and then the hardware starts displaying the image onto the screen, and we see the image. So in terms of a step-by-step, what does this look like? Well, the document change triggers a paint, right? We call it a paint in Blink side. The paint triggers the rasterization by the renderer, so the renderer prepares those SKIA lists and sends them to Viz. The rasterization commands are sent to Viz and generate a new, after they are rendered, generate a new display compositor frame. The display compositor produces a new scan-out buffer with all those new images that we have. And then Ozone DRM, schedules this buffer to be displayed on the screen. And then the kernel driver programs the hardware, says, please show this buffer at these coordinates. And then the actual physical display hardware starts showing the pixel on the screen during the next refresh interval. So that's the high level for a web page. But how does it work, right, for an external application? Let's say in this case an Android application. So I call it life of a Play Store frame because we're going to open the Android Play Store and see what happens. So if you remember the Arc++ part of our big diagram earlier, right? The Arc++ applications, they run in a container, right? And they use the standard graphics stack. So the Android app on the top left, right, starts by calling into GLES, right? And will draw the things that he wants to draw into its private buffer. So at this point, it's a little bit different because the application calls into the 3D API itself to go, hey, I want to show those things. When it's done, it talks to Surface Flinger and says, okay, I'm done with my buffer. Please show this buffer. Surface Flinger goes to the platform-specific part of Surface Flinger, which is Hardware Composer. Like I said, in our case, is a pass-through, which goes to EXO. So again, this buffer traveled from Android app to Surface Flinger to Hardware Composer to EXO, and now is inside of Chrome, same buffer. And then the Chrome side takes care of the compositing, right? And so hopefully we're going to be using an overlay here as well, and it will be fast enough, right? So Chrome gets the buffer, integrates it into its compositing tree, and then shows it on the screen. So on a step-by-step, what does this look like? Well, we have a Play Store application. The user is scrolling through it, right? This triggers the application to render a new frame, so a new buffer, like I said, using OpenGL, for example. Surface Flinger receives the new frame that we have, and it forwards it to our Hardware Composer. Our Hardware Composer, like I said, is a pass-through which talks to Exosphere and say, hey, look, this is the new buffer. Please show it on the screen. Exosphere tell the display compositor, hey, look, I have new content. Can we produce a new frame? The display compositor decides to, for producing this new frame, decides to use a hardware overlay for that application because nothing else is changing on the screen, so it makes sense to do that. Ozone DRM schedule, this Play Store buffer for scan out, right? Among the other buffers that we have, it says, look, I have the main buffer and I have my Play Store buffer inside it. Please scan all these buffers together. So Ozone DRM goes and asks, the kernel DRM to do that. The kernel driver receives those commands and says, okay, I'm going to program the hardware, programs the hardware. Okay, start scanning out those things. And then the display hardware, after one refresh, will start showing the image on the screen. And so a similar use case is how does it work for a gedit frame, right? So if I have a Linux application, what is the life cycle of the buffer here? And it's fairly similar to what R++ does. So if we take, again, a high-level view that we have here, right? In the case of Linux application, the main difference with the previous one is the fact that we run in a virtual machine. So it's a tiny bit more complicated. So the Linux application first talks to Virgil, which is our OpenGL implementation, which tunnels through vertically, as you can see in the diagram, right? Virgil guest kernel, Virgil renderer into the host OpenGLES driver. We tunnel through the rendering, right? But as far as the Linux application is concerned, it's rendering through OpenGL just like it normally would. When it's done, it takes its buffer that has been produced and passes it to XWayland, right, to X11, right? XWayland is basically an X server that on one side gives you the X11 API and on the other side turns it into Wayland, which is convenient because EXO accepts Wayland. So as you can see, we can tunnel from Linux app to Wayland to EXO this way. Then we have a daemon called Sommelier, which is basically the main job that Sommelier does here is to turn the buffer IDs from the VM guest into buffer IDs that the VM host can understand. Because of course, since we're in a virtual machine, the ID spaces are completely different. So we can't mix and match. So we have to translate as we exit, but that's essentially it. So we translate the buffer ID, just this file descriptor, we translate it. EXO receives this file descriptor, but again, there has been no copy here. Receive this file descriptor, integrates it into the compositing tree for including with the rest of the system, other tabs or other apps, etc. And then composites them and shows it on the screen. And again, not a single copy in there. The buffer that the Linux app has produced, unless there's some copy for compositing, is the same buffer that is shown on the screen. So let's go step by step for this use case. The user types in gedit, right? Types some characters. GTK will produce a new frame, right? And like I said, that tunnel's done all the way and back up, but that's almost an implementation detail. When this is done, GTK sends the frame to Xwayland. Xwayland turns around and passes the buffer to Sommelier, right? Sommelier translates those IDs like we talked about before, and then sends the other ID to Exosphere. And at that point, it's exactly what happened before with R++, which is Exosphere produces incurs a new display compositor frame. The display compositor decides, oh, I could use the hardware overlay again. Maybe this is the only application that's moving. Maybe this is the only application that main application on my screen. So we decide to give it a hardware overlay. And then Ozone DRM, schedules displaying that this set of layers that we have, including the gedit buffer for being scanned out. It does so by talking to the kernel driver, which then tells the hardware, hey, please start programming these buffers to become visible at these coordinates, etc. Right? And at the next VBlank, the display hardware starts becoming visible on the screen. So that's essentially the story for Linux applications there and how they render and display. Now let's look at one last use case, which is how do we plug in, what happens when you plug in a display, right? We talked so far about simple case where you have just your one display and you have your app that does something. But what happens when there's a display, arriving here? What's the story? And this is a little bit interesting because it's something that you don't typically have on Chrome, right? Chrome proper. This is Chrome OS specific. That new displays can show up and that Chrome has to manage them. So this new display, when a new display is plugged in, the very first thing that happens on the bottom left here is that the hardware will generate an interrupt, a hardware interrupt. At the hardware level, this is direct effect of the fact that we have physically plugged the display, right? That will make this interrupt happen. The kernel will pick up this interrupt, right? And it will have an interrupt handler, which will turn this interrupt into an event that user space sees and send that event to Ozone. And Ozone will look at the event and say, oh, this is a display change event. I need to send it to the display configurator. So it informs the display configurator, hey, there has been a change of state. So then the display configurator goes and starts querying what's the state of everything, what has happened here, right? What is this new display? Are there other things that have appeared or disappeared since then? What are the capabilities, right? So he looked at all those things, all the numbers and type of displays, etc. And then he makes decision of what do we want to do with this new display, right? At this point, the display still hasn't been turned on, right? All we have is something has changed, there's a new display, but no, we have not affected anything. So display configurator decides, okay, I have a new display. Here are the list of resolution the display can do. I'm going to pick the one I want, right? Pick, the refresh rate I want. I'm going to pick what kind of scaling factor I should use. Should I do some color correction, etc. on this display, right? It will decide all those things. And then Chrome will allocate a buffer for this new display, right? So we can actually render to it. We'll paint a frame, right? We've seen before how we can paint a new frame. And then we have this new frame. We turn around again, like always, we turn to Ozone, right? To try to effect all these changes. So this buffer, along with the request to enable the display at a given resolution and a given refresh rate, all of this information is sent to Ozone. And Ozone turns this into DRM level commands. DRM will take these commands and will start affecting them on the hardware level, programming the hardware, And then at the next time, the next VBlank, the hardware will start sending the data over the cable, and the display will actually turn on. And that's only at that point, after all this big loop, right, that we have. You see this loop going up and down in the diagram. After all this big loop, only then do you have something on your display, right? So it takes a while to get there. There's a lot of complexity. There's another arrow on the top right, which is, yeah, we affect the Chrome OS UI to say, hey, by the way, there's a new display. Please show it in the settings, right? So if we go again if we look at a sequential diagram of what's going on for a monitor hot plug, is what happens. The display is plugged in and it generates a hardware interrupt, right, which is uh, our kickoff, right, for all of this. The kernel produces an event based on that hardware interrupt. The event gets picked up and consumed by Ozone, and Ozone alerts the display configurator saying, hey, something has changed. You have to look at the state and make a decision. So Ozone goes and picks a video mode, picks a resolution, picks all of that for the display. Then we make the buffer, etc. And we go back down to Ozone, right? And we say, hey, can you please set the mode that I've decided? And then Ozone, Ozone programs the DRM level, the kernel level, right? And then the kernel configures the actual hardware to set this video mode. And then the display hardware actually turns on and starts showing pixels on the screen, and we actually see the things. So that's it. Thank you for listening. And if there's any question, I'm more than happy to answer. All right. All right. Should we wrap up?